Hello, and welcome to this session. We're glad you're joining us today. My name is Sally Brooks, and I will be your host for this session. In this section, Dr. Derek Loftis will be talking to us about his and his team's work on forecasting tidal flooding and storm surge. After a short presentation from Derek, we'll have a Q&A session. With that, I'm going to go ahead and turn it over to Derek to get us started.
Hey, thank you very much, Sally. Appreciate that introduction. The title of my talk is focused on coastal resilience and tidal forecasting, and relatively focused on some of my research efforts at VIMS focused on storm surge. So one of the real challenges that's involved when you're trying to map tidal flooding is, of course, you've got a combination of observations that help us validate the accuracy of predictive models for things like tidal flooding. In this example of Norfolk's Hague region that you can kind of see in the background, water levels that exceed 4 feet above mean low or low water, i.e. when that line in the foreground becomes red, you'll start to see a lot of inundation take place in Hampton Roads, Virginia, but also many other coastal areas throughout the eastern coast of the United States. And some of the challenges that usually entails is that you've got a lot of vehicles that suddenly can't cross low-lying intersections and roadways. And so the line that's in the foreground is essentially representing water levels at the Sewell's Point gauge in Norfolk, which is a water level sensor that's been maintained by the National Ocean Service and the National Oceanic and Atmospheric Administration for nearly the last 90 years. Now, the data that we can collect from these types of sensors provides us profound information in terms of being able to validate the accuracy of flood forecast models that we develop here at the Virginia Institute of Marine Science. So I'll be talking with you today a little bit about how exactly we go about flood forecasting, both tidal events, which are kind of a pervasive issue that occur pretty frequently year-round, most frequently in the fall and spring, and usually involve the astronomical high tide being the driving factor, but also wind-driven events like hurricanes. And in this case, we also will talk about nor'easters and how we've got long-term wind effects blowing in the same direction, causing wind-driven setup that will induce inundation in certain areas. Towards the end of my talk, I'll also talk about how you can potentially get involved in one of our tidal flood mapping efforts called Catch the King, which focuses on mapping king tides. Obviously, you can see in the foreground with this water level sensors values being shown here over the last several years. We've actually had citizen scientists go out and map individual events represented by these blue dots that are labeled. In some of these cases, there are hurricanes, some of them are nor'easters, in other cases, they're simple tidal flooding. In each of these events, we'll use sensors along with citizen scientists to help validate the accuracy of our hydrodynamic models and use those data to help us improve our predictive efforts in the future. So briefly in my talk, I'm going to go through how our inundation models work at VIMS, where you can find them online and what we can learn from them, but also a program that I've launched in 2017 called StormSense and where those sensors operate. These are low-cost water level sensors that are driven by mobile broadband technology for communications, and they use solar panels to help provide renewable energy in terms of being able to stay online even when we lose power, which is pretty frequent during hurricane and storm surge events. And finally, I'll talk to you about how you can get involved with Catch the King and help us improve our models in the future. On the left-hand side, you can kind of see this is a background of the Larchmont neighborhood in the city of Norfolk. You can kind of see a hatch-marked grid that's represented there. This is an actual hydrodynamic model grid for one of our street-level predictive models. It embeds buildings and all kinds of other fun things into the model to represent accurate volume displacement. And the images on the right are essentially data that I've used and collected myself, along with myself in the bottom right-hand corner there, as we've gone through the process of helping validate the accuracy of our predictive models. Our models will provide us forecasts, and then I actually go out into the field and collect data. And now we've enlisted a large contingent of citizen scientists that help us validate the accuracy of not just our near-term models, looking in the next 36 hours forward, like our TideWatch products, but also long-term predictive models that look at sea level rise and the impact somewhere between 4 to 8 millimeters per year of projected sea level rise, depending on which projections you're looking at. So a talk after mine led by Pam Mason from the Center for Coastal Resources Management, where I also work at VIMS. She's going to talk to you about the Adapt Virginia portal, where you can find more information about exactly what are the differences between the National Oceanic and Atmospheric Administration's projections of future sea level rise and how they compare with those from the U.S. Army Corps of Engineers. And then ultimately, the lines that you can see on the top left-hand side of that graph represent historical storms of note, like Hurricane Irene in 2011 or Hurricane Isabel in 2003, and what storm surge compounded with future sea level rise during a mean tide in those years might look like in the future, because rising sea levels also exacerbate the impacts of hurricanes driving storm surge into our local communities. So I'm going to lead things off with a video that talk about and explain exactly how our flood predictive models work in VIMS.
A few years ago, we had a couple decent-sized storms that come through, and those do cause a lot of challenges for us, but they're not the Katrinas and the Sandys, right? And that's where we want to make sure when those do come, we've got it right.
Storm surge is an elevated surface of the sea level that is brought with basically the eye of a hurricane. For example, the low pressure center means the water can stack up a little bit higher in elevation, and it pushes its way into our rivers, estuaries, streams, and then ultimately our backyard, city streets, and alleyways.
That's one of our goals working with VIMS, is to get the data into the model and get the model results back out in all the ways that folks are taking in information today. If we can get it to them prior to the event happening, that we think can reduce a lot of the risk and damages and issues that we face when it comes.
The Schism model, developed by Dr. Joseph Zhang here at VIMS, and it's a truly unique open source model that's really kind of community built. We've mostly talked about water quality in conjunction with storm surge. What happens when you have a major storm event flush into the city storm drain systems and what comes back out.
I started a developing model more than 20 years ago. Schism right now is really a modeling system. It's not just a model. It's a modeling system that covers the circulation, which includes the storm surge, but also includes sediment transport, ice dynamics, water quality, biogeochemistry, wind wave. The model is really the heart or the engine of the forecast.
The model is used for a variety of different influences, from near shore to far shore to inland, riverine environments are all capabilities the Schism model has.
Modeling is increasingly becoming more important. We're recognizing the value it brings to the table. We want to be that coastal community of the future that other cities can come model themselves after. But you need this data, you need these sensors, you need the data analyzed by folks like VIMS and done right. It's really exciting to have this kind of resource this close to our city.
I think in the future, we probably should prepare for stronger and more frequent storms. Our model can help plan for resiliency, not only for the human populations, but also for the ecosystem. So I'm working with other scientists in VIMS and Winnie Mary to use models to study how the future ecosystem will evolve.
So as the video is illustrated, essentially we drive a street-level hydrodynamic model that covers a large section of the western bank of the Atlantic Ocean basin, along with the Gulf of Mexico. This allows us to trap any particular hurricanes within the hydrodynamic model grids that we run to help us drive storm surge effects into our local communities and be able to actually effectively model and predict them in advance. So the relative shape of our model is roughly 2.3 million points and 1.5 million elements. This is a geometric grid that allows us to represent the relative influences of atmospheric data, but also storm surge from any given direction that it may approach Virginia or the eastern seaboard. So anywhere along the mid-Atlantic bight, we have a large amount of resolution that can represent. Then at the city scale, we have subgrid models that are built for those that you can see on the right-hand side, like those for the city of Norfolk and Portsmouth. We have some for Virginia Beach and some in counties in North Carolina as well. The buildings are directly resolved within those models to further refine some of the impacts of not just sea level rise and land subsidence, but also storm drainage systems that tend to back up and the types of effects that those might have. So to get into a little bit more detail on exactly how communities use these data, this is a view of our Tide Watch forecast. It's available on the DAP Virginia portal. It ingests 2.4 gigabytes of atmospheric data at 3-kilometer spatial resolution every time that we run this model. And it does this to predict storm surge that's induced throughout coastal Virginia up to 36 hours in advance. You can kind of see the time slider on the bottom of the map there as we're zoomed into a creek that leads back to the William and Mary main campus in Williamsburg, Virginia. Now it does this everywhere in Virginia's tidewater region at approximately 3 foot or 1 meter resolution spatially, and temporally the model is run twice daily at noon and midnight. So as a result, when it updates twice daily, this gives us a series of overlapping prediction windows that allow us to have at minimum a 24-hour forecast and a maximum up to a 36-hour forecast looking forward, as the model updates every 12 hours with the newest data from the National Weather Service. Now, each of these simulations is a 36-hour simulation that takes 1.25 real hours to run using 72 high-performance computing nodes on the Schism's main nets, both on the VIMS campus and the William and Mary Cyclone system. And it does this effectively to visualize tomorrow's flooding today on a web-compatible browser without you having to have any specific software to be able to run this. You can view this in any web browser. And the utility behind this naturally is that you can click on different places on land and it can actually tell you what is the water elevation every hour for the next 36 hours. And any places that you see this blue line intersect this yellow line representing land elevations, it automatically imports the land at whatever place that you happen to click, whatever its elevation is. And when you see the blue line exceed the value of that yellow line representing the land surface, it tells you how deep that water will be in some of these places. So in this example, you can see somewhere approximately 24 to 26 hours from now, the road surface that was clicked on in this map will have somewhere between 3/4 of a foot and almost as much as 1 foot of water standing in the middle of the roadway in this particular area, as predicted by our Schism hydrodynamic model, visualized through our Tide Watch map on the Adapt Virginia Porter. Check this video out to talk about exactly how tidal flooding works. VIMS has done quite a bit of work with the city of Portsmouth and city of Norfolk to support their comprehensive long-term planning.
You know, people associate hurricanes with flooding and things like this. The hurricane is one thing, it comes in, it blows for a day and a half, and it leaves. The flooding is what you deal with long-term.
So Tide Watch is a 36-hour tidal forecasting system. Tide Watch can be used by the everyday person by going to the Tide Watch page on the VIMS website. You can select an individual gauge site on the map and it will tell you what the water level is going to be 36 hours in the future. And so each of these gauges have different data that they're feeding into the system. And so in many cases, we found that Tide Watch is more accurate than many of the other different types of tidal predictors by taking into account that relatively recent period of history at that gauge.
We've been exposed to it and think it's tremendous information. It's something that should be spread far through this area.
For our community, it would help people decide whether to get the heck out of Dodge or not. Well, like you drove by here yesterday afternoon, and this was
5:30,
and this was dry as a bone. Look at it now.
I mean, other than a couple of little puddles, there was nothing. Now the entire place is completely underwater.
So each individual place in the Tide Watch program is important because it gives a better understanding of not only what is the tide there, but Tide Watch also incorporates some loose surge guidance based on a series of separate models.
And we integrate those together onto a single page on the VIMS website, so they're accessible. This is so visual that you literally can see whether or not particular roads are expected to be flooded. Our intent, and we're working towards it, is to extend this to the entirety of Tidewater, Virginia.
So this product can be found on the Adapt Virginia portal, and I'm just mostly talking about specifically the forecasts page. If you want to hear more about all the different utilities that website has at adaptva.org, tune in to the next talk after mine, led by Pam Mason, where she'll talk to you a little bit more about the sea level report cards among the many other utilities the Tide Watch products provide, but also those within the Adapt Virginia portal. In terms of the water level sensors, we have both hydrodynamic models that drive forecasts, but also sensor-driven guidance as well, using harmonic decomposition. This basically looks at the sun and the moon's influences on the tides, looks at the past data, and then projects forward this dashed red line as to what we anticipate the water levels to be over the next 36 hours. And while the Tide Watch base program had approximately 10 water level sensors driven by the federal government, we now have many state-maintained sensors and several local government-maintained sensors through the StormSense program, like this example in Newport News, near one of their facilities just north of the shipyard. And these data help us better anticipate the relative impacts of our schism model in certain places and its relative validity in the data that it predicts in real time. This program's garnered many awards over the last several years, including those from Amazon Web Services, which helped us kind of get our start. And they've been awarded to the different cities that we've been able to install sensors in, including most recently winning 2 Virginia Governor's Technology Awards in 2019 for automated alerts that are driven by these sensors. So if you live in the city of Newport News, for example, you can sign up for their NN alert system, and the Newport News alerts will go out whenever water exceeds a pre-established critical threshold at those sensors in real time. And so these have been proven quite useful during Hurricane Dorian in 2019. You may have also heard about some of the research that VIMS has been doing in this space in terms of citizen science. You can't just put sensors everywhere. They cost money to maintain. And they're also, even though the technology costs are going down quite a bit, we've also found that we've got very engaged citizens that are particularly interested in the impacts of flooding. And so there's been a couple of very popular events that have happened over the last couple of years called Catch the King that's been covered by individuals like famous oceanographer Don Wright, who is the chief of science over at Esri, who develops the GIS platforms for geographic information systems, the largest software platform in the world for that, but also Science Friday with Ira Flato. I was on NPR last year to talk about that. Also, CBS This Morning covered us in 2020, covering the last several years worth of data that we collected in Norfolk. And most recently, in fall of 2020, leading up to Catch the King this past year, we were on the Weather Channel several times to talk about some of our efforts and exactly describing what king tides are for most of the Atlantic Eastern seaboard. Now, the benefit behind this approach is that it's not just me validating the model anymore. You're able to recruit a large number of individuals all over coastal Virginia to help us validate the TideWatch products that we've developed. So you can see here in Rudy Inlet and Virginia Beach, the king tide doesn't happen simultaneously everywhere. So tidal flooding becomes important because it's flooding that we deal with more frequently than just the occasional hurricane, which markedly produces more flooding, but occurs very quickly, as was noted in the video. Now you can see all these blue dots appearing on the map. We collected many, many data points to help us validate our models in large sections of coastal Virginia very quickly. And this is all taking place during a single tidal cycle. And of particular note, I applied on behalf of VIMS back in 2019, and we were awarded the Guinness World Record for the world's largest environmental survey, where we collected nearly 60,000 GPS data points with the assistance of over 800 individuals in a 6-hour period of time on November 5th, 2017. Now, this event has happened annually since then, and it's allowed us to improve the predictions of our models. On the left-hand side, you'll see a series of basically GPS breadcrumbs that people have taken their GPS-enabled mobile devices and walked along the wet-dry interface during a king tide. Thankfully, tidal flooding is relatively safe for you to map. There's not strong winds. They're usually referred to as blue sky flooding, and people will post them on our Catch the King Facebook group called Help Catch the King Tide. There's over 1,000 members in that group, and they'll usually post regularly when there's flooding happening somewhere in coastal Virginia. And the core ask behind this group is really, I will post occasionally some of our flood forecasts in the near future and say, hey, in the next 24 to 36 hours, there's flooding expected in these places. Is anyone interested in going out to snap pictures or upload GPS breadcrumbs as they produce digital contours of what the maximum flooding extent was? And then as you can see in the red line, we kind of go back and trace through a lot of these areas. And while that shape doesn't always perfectly match, because of course some of these are private properties, we're not going to have volunteers walking to other people's fenced backyards in order to collect these data, it does help us confirm in real time exactly what the flooding looks like. But also the key element that this adds is it also helps us improve our hydrodynamic models during these low stakes situations, like during a king tide. For example, this is a non-tidal creek in the city of Virginia Beach called Pleasure House Creek. And in our initial king tide measurements in 2017, some of our citizen scientists actually went out there and mapped and said, hey, the water level is not normally this high in this space. And it turns out that the aerial survey data based on LIDAR, basically lasers from aircraft that help us produce digital elevation models that represent the surface of the earth in our digital models, ended up representing a virtual dam underneath this bridge. And so water couldn't flow beneath the culverts in this bridge to be able to flow through into this creek that is not normally tidal. During the highest astronomical tide of the year, there's flooding that took place. Our model incorrectly predicted this the first time. And so as a result, we were able to go back and correct the digital elevation model before more significant flood events took place, like a major hurricane, for example. In many ways that we do this is essentially measuring linear distances between the blue points that are collected by our volunteers. And you can even see the dark space that's represented in this image, where you can clearly see standing water usually is pretty pervasive in the backyards of these neighborhoods in the city of Norfolk. Again, it takes the correction of basically removing some street space and allowing culverts to have free flowing water through them in order for our model to correctly predict these things. At this time, are there any questions? Thank you for your attention.
Thank you, Derek. That was great. I'll just kind of go ahead, Derek, and get started with, does this model, you mentioned that it kind of covers a big area, but is it only kind of in the tidewater area of Chesapeake Bay here, or does it cover a larger area?
So king tides affects all of the Atlantic eastern seaboard along with the Gulf of Mexico. The relative frequency of these floods are a little bit different. For example, here on the East Coast, we have a semi-diurnal tide, so we'll have 2 high tides and 2 low tides per year. So the likelihood of landing on a tidal peak for some of these events is a little bit higher when there are 2 peaks per day rather than 1. So you kind of wind up with these combined effects of maybe it happens to land during a significant rainfall event, and as a result, the flooding is worse because of that. Or in some cases, just strong winds, either during a nor'easter or during a hurricane, are more likely to land during that period of time as well. Whereas the Gulf Coast also deals with these, but they're slightly less frequent because they have 1 high tide and 1 low tide per day, since they are a diurnal tidal cycle there. But king tides are issues all throughout the world. On the Atlantic East Coast, we deal with them a little bit more than most, simply due to the oceanic gyre in the Atlantic that kind of drives what we call Western intensification in terms of physical oceanography. The cycle of the Atlantic Ocean basically brings a lot of the water directly adjacent to the coast. On our side of the basin, just due to the direction the planet spins. And so as a result, you'll have western banks of oceans more heavily affected than eastern banks. So the same issues you'll see on the coasts of China all the way on down to Thailand as well.
Okay, great. And if somebody wants to get involved with the Catch the King program, how do they go about doing that?
So usually it's pretty easy just to Google Catch the King. It usually pops up with the first several different posts. We have a VIMS webpage where you can just search the VIMS website for Catch the King. I maintain several pages for each year's data set, and the data are publicly accessible for individuals to interact with their own personal projects as well. So our goal is not just to be the only researchers that make use of these data, but to share them with our other institutional partners within Virginia, and also encourage other states to get involved in producing their own products to track high tides throughout their area.
Great. Okay, we have a question. Are the frequency and/or lengths of the flooding from tides changing in recent years?
So that's a good question, because some of the challenges that are involved with that is, you do have more frequent tides. I don't know about the lengths of the tides themselves. The tidal cycle is still usually about 6 hours between each high and low tide, or a 12.42 hour cycle for a full wavelength of the tide, including a high and a low. That hasn't really changed. So in terms of the length of the high tides, that's not really getting much longer beyond the impact that you would expect with increased amplitude. So as the water levels increase, the amount that's required to flood a roadway, yes, slightly gets a little bit longer, but the tides themselves are not getting any longer. Just the amount that they breach onto the land is increasing as their amplitude increases.
Well, I think we are about out of time. Thank you, Derek, for being here and talking about your and your group's work in forecasting tidal flooding. And thank you all for joining us.